Matt, thank you very much for coming today. I have here a micro CV of you, so which I will read. So I think you are at Kitware still in North
Yes.
Carolina in the medical computing team. Then I read something that I didn't know, that you are specialized in diagnostic ultrasound imaging with an emphasis on radio frequency-based signal characterization. So that's entirely new to me. So I don't know whether we will hear anything about that today. Then what I know you for is that you are leading the development of ITK, a high-performance n-dimensional image processing library written in C++ with interfaces in Python and JavaScript. So that's obviously a big thing. And then recently you became more interested in WebAssembly, um, ITK.js, so I guess wrapping ITK in JavaScript or something like that. Let's see. And then also what I mainly thought I invited you for, but of course happy to hear anything else also about all the nice web viewers that you recently built. Okay, so thank you very much. And then, yeah, take it away, Matt. Very curious to hear what your vision and stuff is.
Thank you so much, Christian. And I'm very, very happy to be with you. And thank you so much to Christian and Nikita and Robert who are having me. I'm very happy to be with you, and it's an honor to be with you. And I'm excited to talk with you about this idea, really, of progressive bioimaging on the web. As Christian said, years ago, this started and formed um, as a path forward, and it's really progressed, and I think it will progress more. But I want to share a bit of this concept and some of the work I've been doing along these lines. So we'll go beyond my audio description into a little bit of imaging description and visualization you see on the right of what progressive bioimaging on the web can look like. This is produced by ChatGPT, so it's fairly accurate of kind of what that might look like, but I'd like to get into more details of what exactly this idea of progressive bioimaging on the web means and how we can actually achieve that vision. So as Christian said, and I know I met a number of you, but many of you might not be familiar with me and my background and my story. I've been involved with the bioimaging community for many years, taking part in the I2K workshops and participating and meeting many of you in different hackathons together. My background is, as Christian was saying, was ultrasound imaging and medical physics and bioimaging. And so I worked with energy in terms of ultrasound waves, and I've moved beyond that to working with many different types of energies, light and beyond, as many of you do, and working material science in different scientific domains, chemistry, medical imaging. But more recently, a lot of my work is focused on microscopy, bioimaging, neuroscience specifically. And I work at Kitware, an open source scientific computing company, and I contribute and work with all different sorts of scientific computing projects, open source scientific computing projects as a research software engineer. A lot of my focus is on the Insight toolkit that I work with. I worked with in my PhD, and I continue to work with today. And this is a cross-platform and dimensional image analysis toolkit that's been around for a few decades, working on spatial algorithms for scientific imaging registration. If you might have used some of the registration tools that are based on the Insight toolkit. It has a large community, and we are now a nonprofit under NumFocus, too, like Julia and some of the other folks there at Genelia are participating too. And I work through this company Kitware, and if you're not familiar with Kitware, it's a scientific software computing company that works on open source tools and platforms and applications in a way that we collaborate with the academics and the people in government labs and the people who are doing commercial products based on these platforms, with the goal to produce sustainable, high quality computing solutions that help us understand the world through science. And it's a services collaborative. We provide services to the people we work with. And generally, the idea at Kitware has been in the past, create these and support these community-based universal open source platforms. And a few decades and then it evolved a bit to be working on mobile, working on cloud and HPC beyond just the desktop. And more recently, it means the ultimate universal platform, which is the web platform as it's known. So today I'm going to focus a bit on the web platform and specifically the idea of progressive web apps for bioimaging. And you see here again another ChatGPT imagination imaging rendering of what progressive web apps for bioimaging looks like, where you're taking and exploring this universe of data in a 3D environment, and you're continuously discovering the vast scale of data that we have to deal with in the digital age. That's what ChatGPT says. But what exactly does that mean? Progressive web app first, have an understanding of what is a progressive web app before we do progressive bioimaging. So I'd like to go through that with you by experience with an example. So here is a progressive web-based bioimage viewer. I'd recommend, if possible, you can scan that QR code on your phone with your camera, which is quite easy. This will be, if you can also click on this link, I'll provide a link to the slides in the chat here for people who can follow along. This is going to render a cells of an embryo hosted at EMBL there, at ABI. And so, again, participation is highly encouraged. I'm going to share in the chat. I can get the chat here. The presentation. But just using your scanner on your phone. So please take a moment to do that. And when you do that, it will load up this data, and this is a progressive web app. And what exactly does that mean as a progressive web app? So one, it takes you to a web page, but it's not just a static web page. It's a web page that provides advanced functionality like an application, but you didn't have to install anything, which is extremely convenient. The other neat thing about this page that making it a progressive web app is, if you're on your phone, you can go to the menu and say, add to home screen. There's an option. And that will put a little icon on your home screen, just like any of the other applications you have on your system, native applications. So it's behaving then just like a native application. The nice thing, though, is that you didn't have to explicitly install anything, go through any more difficult installation steps. What else makes it a web app instead of just a web page that you go to?
Sorry, Matt, where was that thing where you added to your?
At least on Android. I'm not sure about the iPhones, but in the Chrome browser, like if you click the
On
three
the
dots
phone, not on the computer. Okay.
on the phone, yes,
Oh, yeah,
yeah.
yeah, yeah.
And I think on some computers, like if you have a Chromebook, this might work
Okay, okay, cool,
too.
cool.
So, and these are open standards that this is based on. You'll get this icon just like any your other apps, and then after you've installed and started using it, it's actually installed on your system without any other steps, and it can work offline. And you can load up local data on the system, so it's working again like a web app, and it can use the native system resources or capabilities when they're available. So our browser isn't just this passive, very limited system. It can also load local data or even work with hardware like your camera. So you can look at your own data from that camera. So really what we'd like to talk about today is not just how do we do bioimaging on the web when we say progressive web apps, but this concept and this practice of possibly starting in a web browser with people's experience with their data, and then progressively giving them all the capabilities that they have had with traditional computational systems over the last few decades. And how do we do that? And this is extremely appropriate and helpful for science and research, because today we often have this situation where we're acquiring the data on a microscope somewhere that's in a fixed location, but we also have to do compute with these very expensive resources that are located in other places, like the laboratory workstation or on the AWS cloud or a cluster. And we would like to interact with that data. And the best way to do that is a web browser, either at home, or if we're in nice North Carolina here, like where I am, if you want to understand and we don't want to stay away from COVID, we can do that through a web browser. And since we are focusing on research, that means we have to focus on reproducibility. And so I'd like to look at what does bioimaging mean, progressive bioimaging in different dimensions and in different dimensions of open science, really. So first look at, how do we do progressive bioimaging in terms of the data that we're working with? Then in terms of working with the computing resources that we have. And finally, in terms of the code, the analysis code that we work with, how do we bring these concepts to practice? So starting with data, the practice is really the work that you all have done at Genelia and EMBO on these new formats. They really power a lot of these possibilities, like OMISAR and M5, and through this hierarchical and dimensional arrays with metadata, and also this multi-scale image model, and these compressed chunks. Really, that approach enables this functionality on the web, looking at these very large scale data sets in a remote way, in an effective way, either with 2D view visualizations or 3D visualizations. Because you have all these properties of being multi-scale, chunked, the efficient compression, the web-friendly formats, the hierarchical nature, the separation of metadata and bulk data, and the universal standard cross-language support of these standards, that is really enabling a lot of this work. It enables us to do what the traditional computing community has focused on for the last few decades, to make the web experience, the web platform, as powerful as a native platform. And this technology and community and ecosystem of tools enables us to create an effective web computing platform because it gives us the ability to load progressively the data and give a progressive experience with the data. So inside your browser, and most web programmers who work on non-scientific data, they focus on these metrics that are part of the Google Core Web Vitals, what they call them, that they are the metrics that they've determined that define the business value of a website web application. And those are things like the delay to the first, be able to make your first input on a website. And then also how consistent is the experience on the website as it progressively loads. Largest contentful paint, community layout shift. So that is what we're going for, and that's what's enabled by these technologies. In the business world, those are metrics on how much value your application is having. And in terms of the scientific world, this is enabling us to get as much knowledge as we can out of the data, and I think in a similar way. And we can do that with these tools that progressively, if we're visualizing the data, load it from 2D to 3D. Neuroglancer, I think, is one tool that comes to mind, especially taking us from this tiled loading experience of MapQuest or Google Maps, but with these scientific microscopy data sets. And we've done some work with a focus on volume rendering, loading the data from low resolution to high resolution, so you get to experience it as quick as possible and get to interact with it in 3D. And some of the approaches and tricks that we found that works very well for working with this data. When you load the data in one of these interactive viewers, you have the scale that you can select manually, but we also have the behavior that it will start off at the lowest resolution, progressively load, but it will take advantage of what your hardware, your individual hardware capabilities are. So it'll load up with limits on until you get to a point where the frame rate is non-interactive, and it'll back off. And it also have checks on, if you're doing client-side rendering, what's a reasonable amount of data to load in memory, or if you're doing remote rendering, what is the memory capabilities of your remote GPU. And then again, as you have the ability to select a smaller region of interest to focus on, and then when you select that region of interest, you can again zoom in and get a higher resolution of the data. So progressively looking at parts of the data in this way. That's some ideas and ways to go with progressive open data, low resolution to high resolution, and using some of these standard next generation file formats that the community has come up with. Another aspect that we can look at this idea is the compute, and how do we provide the compute in a way that's enables this progressive applications. And Christian and I were talking before we started here a little bit on how do you do that in a practical way with our data, and performance is the way to do that, and taking advantage of some of these new technologies, as someone said before, like WebAssembly and WebGPU. And these are very high performant technologies, even though they're on the web platform, and they've taken a while to develop so that they work universally, but they're coming, and they're coming support into browsers, into and also on systems too. Things like SIMD, single structural multi-data, support on processors, support for threading, support for GPUs like WebGPU. And an important way to approach this too is, as these technologies come on, have support all the time for just JavaScript, but then enable support when possible for these other technologies like threads or web GPU when they're available, even though they might not be available everywhere. So that's a strategy to take there. And then update the code with these systems progressively
Matt,
too. Yes.
Matt, I have a question.
Yeah.
Well, the nice thing about WebAssembly is that there's multiple ways to get into this, not just JavaScript. And so maybe returning to the beginning with what Christian was mentioning, is JavaScript the best way to do this still?
In terms of what language to use.
Right. I mean,
Yes,
would
yeah. I
it
mean
be better
that's a great question.
yeah.
And what languages are supported by web browsers? And when we talked about this, Christian and I, many years ago, the answer was, well, web browsers only support JavaScript, so JavaScript is really what you have to focus on. And that's changed a bit. So now that effectively JavaScript or browsers support JavaScript, but they also support WebAssembly. And WebAssembly is not a language in itself, but it's a compilation target that almost all languages now support. So, and it also has better performance. So I think the answer has evolved there to anything that can be compiled into WebAssembly, even though JavaScript is certainly still important as kind of a bridge and a glue in many cases. Would you agree with that, or do you have additional thoughts?
Yeah, I think so. It's as you mentioned, it's a compiler target. So some languages like Rust and Sig can now target it, and so I think those are, and I think also Go as well. So these are really interesting languages that have inherent concurrency support. That may allow people to use more traditional development methods, but now deploy this into the browser. And I think that's extremely interesting. Um, and actually, one of the latest things I've seen in WebAssembly is they just implemented garbage collection support. And so, putting my other hat on, there's increasingly Julia support now for this as well. So I think we're going to see quite the explosion of these
It's evolving to
technologies.
support almost all languages, like the garbage collection for Go. I don't know about like Julia or other languages, but getting more efficient and having more capabilities. And you're right, all these different languages compiling for the web. But we'll also talk about in a little bit too, or for the web browser. But it's a target that can also be used beyond the web browser, which is quite exciting on systems. And then the other really unique and transformational approach and idea that's coming from the WebAssembly community is that you can have different WebAssembly compiled from different languages talk to each other directly, which is fairly revolutionary, I think.
Yeah. So I was just curious, have you tried anything else other than JavaScript so far, or?
Yeah, so I've done, and we'll talk about it in a little bit, but I've done
Sure.
compiling the JavaScript and TypeScript bindings, but also Python that runs on the system or in the browser. And we also had a hackathon recently with Curtis. Curtis Rudin was there, and he helped bootstrap some of the Java support. So the C++ working in any Java runtime. And
Great.
and I think there's a lot more that we could do together, and I think it's very exciting. I would love to work with you all if you're together on this in these different languages and these different applications. I think it's extremely exciting, like you said, to have that potential of working just not on the browser, but this idea with these applications and working on systems. So talk about that a little bit more as we go. But just to come back to this idea of in the browser, there is this kind of technology that you can be aware of that helps make this offline support possible. And so how do you go from no installation to having something that works on your system with offline. It's there's this technology called a service worker that works in your browser that's now available, where you go to a web page and then it's essentially caching this application for you, and then it works online, and it seems it's very transparent in that this process of having something that works locally without installation. And another approach that I found very helpful in terms of uh, creating these systems that work not only locally on your local system, but give you access to workstations or cloud computing clusters or high performance computing clusters that you have, is a lot of collaborations with Wang on this ImJoy platform, and now Kaibu is another system that allows you to do remote procedure calls, but it also is done in a way that it's very easy and appropriate for working with scientific computing languages and systems, and flexible and powerful. It's extremely powerful, programming in Python, for example. That's something we use a lot, and it allows us to have this capability to render those embryo cells locally on client side, but then have the ability to do some more advanced rendering, progress into more advanced server-side rendering, where you need more complex software stack and maybe some specialized hardware like a GPU. So using those tools, you can go from this pure client side into something where, using the same data, you're doing remote rendering. And down on the lower right here, we see that same data set, but rendered with the Agave renderer, path traced rendering from the Allen Institute for Cell Science. And so that's in progress. We have this project based on this work and these experiences called ITK Viewer, and this is a piece that can be used inside your other applications, web applications. Develop your own user interface on front of it and embed into your web application, built with your own technologies, but also have customizable renderers in the back end, based on different technologies, either client side or server side. And so you see up on the top here, we're seeing two different interfaces that are written in different frameworks on the front end, or not a framework, just JavaScript. And then in this middle screenshot here, we see an application where the viewer is embedded into a larger web application that's based on helping doing machine learning, providing visualization as you're developing your AI pipeline, TensorBoard with TensorBoard. So this gives us the capability to, when we have some data set and a bioimage analysis wants to come in and interact with the data, if they want to look at some data that's already been exported and pre-processed into OmniZar, for example, they can do that immediately. And then if they have some new data, maybe it's not in OmniZar, they can put it into their web browser, and WebAssembly, it will generate this multi-scale chunk pyramid for us. Or if they want to go further and they want to work with server-side resources, they can do the same with Python on a server and use some specialized compute resources for doing some further investigation, working with your other software tools, your other data sets, doing more advanced analysis, and being able to, in the end, get this custom exploration of the data with all the compute resources that you have available, is the idea. So Compute Progressive idea is taking and using these more advanced browser-based technologies as they're available. They might not all be available right now, but they're more and more becoming available, and then also progressively getting access to these remote resources like clusters. And ImJoin and Kaibu can be helpful with that, also ITK Viewer. And finally, I'd like to take a look at code and what progressive bioimaging for research means for code. And when we talk about code for open science, reproducible research. And this is, I think, similar if you have the journal Science. If you've read or written any of these journal science articles, they start off with something that's very high level and you can understand and get some value out of them. And then they progress into more details that require more context of a certain domain, or maybe some very in-depth mathematics that not everyone may have access to. And we can take that same approach really with the computational resources and the code we have, so that we get progressive value scientifically out of the data. And we can start by having a simple web application that anyone can use, and it's a very low effort from their end to get the basic information out of the data. And then with that same technology, we can provide for them, if they know basic coding or they want or have the need to do some more in-depth analysis on the data, you can provide for them a Jupyter notebook that they can work with this data remotely in the browser and do some basic coding. We use this client-side ITK viewer, and then there's this project we've been working on called ITK widgets that provides a Python interface to bridge with this data set with these same technologies and use them within the rest of your environment. And then we can take that even further so that you can use all the different programming languages and all the different libraries and all the different pieces of the scientific computing ecosystem, like we're talking before. And that work a lot of my work has been focused on this project called ITK WASM, which is WebAssembly, and it's WebAssembly that works in the browser, but also on systems. So there's this technology that is coming called WASI, which stands for the WebAssembly System Interface. Some people have also called it recently the WebAssembly Interoperability Interface. So that takes this WebAssembly, allows you to run it on systems and embed it in languages. So the C+ code in this case can be run in the browser through JavaScript or TypeScript bindings, but it can also be run in the browser through Python bindings for the browser, but also Python that runs on the system. You can run it on the command line, these WebAssembly modules. And from the ITK part of it, since ITK is written in C++, we generate these C++ modules. But there's also coming in the WebAssembly community this idea, it's called the WebAssembly component model. And that's taking these WebAssembly modules and allowing you to use together different WebAssembly models, like we're talking before, that were written in different languages, but have them interoperate with each other. And so you can have different components of a processing pipeline, maybe coming from even different languages, different components from in a web viewer. So kind of the idea with our viewer is that the logic of the viewer is written in JavaScript, but you can compile it to, eventually the goal is to compile it to WebAssembly and then have a rendering system, a rendering technique be written in any other language, and have your front end be written in Python. So that is kind of the capability and kind of where this is going to working everywhere. And some of the projects that I'm working now that try to put this in practice are like some bioimages that come from synchrotron micro-CT, so these larger data sets, larger than memory data sets. And in there you have the workflow where you have the microscope and on the beamline, and it's generating all this data. You want to kind of get a preview of the data, but then you support pre-processing it into OMIs-R. And then when people want to understand the data, they can go to the website and kind of see what that data set looks like. And if they want to dive in further, they can use Jupyter. And in this case, we have the NERSC supercomputer at Berkeley. And they can programmatically explore the data if they need to and analyze it in any way that they want to, all through a web browser here. So that kind of summarizes in these different areas of open data, working with our different compute resources, and then programming, analyzing our data computationally, how we can do this progressive bioimaging approach. With code, the idea is you have an app, then maybe you go to something more advanced for coding, some basic coding, like a Jupyter notebook, and then eventually the goal is to be able to bring in any scientific software from any programming language and use those capabilities to gain insights into your data and get a better understanding of your data. ITK WASM and ITK widgets are a few of the projects that I'm working on in that area. So many of these data sets, they're working with a lot of the data that you all have produced and helped work with. You can click on some of these links to reproduce some of the renderings you see in these slides. And here's a link to some of the open source projects that support some of this work, like ITK WASM and ITK widgets. HIFA is this application for working with remote data. Some NGFSR work that I've worked on to contribute to the ecosystem in Python specifically. This project here, it's intended to be this NGFSR is intended to be at this universality, this web functionality in mind. So as something that works everywhere, it's very small, but then progressive, we're working on adding progressively. If you have a GPU, you can take advantage of that GPU, for example. And another maybe helpful link here is this workshop at one of the ITK, our I2K Images to Knowledge events we had, and that looks at all these different topics of web-based computing, web-based bioimaging. So to summarize, what did we explore today? One was what is a progressive web app and how does that apply to progressive bioimaging? So the concept is you visit a web page for a progressive web app, and then this web page is transforming into a traditional application with the functionality that you have on the system. And that has been shown to be powerful and effective and practice way of doing computing. And how do we do that specifically when we're looking at bioimaging? Well, these technologies like WebAssembly that everyone pointed out is extremely important. And it's important for doing this computing not only in the browser, but also on the system, and giving people the opportunity to get a lot of value out of your data from simple interactions and exploration all the way down to very highly complex secondary analysis with all of your computing tools to learn more from your data. And we do that with a focus on these high performance technologies, remote and local resources, and then working with the data so that we can work with these large scale data sets we have recently coming to our plates, moving from low dimension to high dimension data with the rendering. So that's my take on progressive bioimaging. I'm interested to hear all of your thoughts.
Thank you, Matt. Any questions?
I had a few down in the weeds graphics questions, if you will.
Sure, yeah.
I'm a big fan of global illumination with nice shading and shadows to help bring out the shapes of complicated three-dimensional data. And you mentioned Agave with its path tracing approach. I can't remember if it's doing that in the client or remotely, but I'd be interested in your take on that approach versus something like screen space ambient occlusion being done in the client as a way of getting some of the higher quality shading and shadows with less computation.
That's a great question. And I think there's many different aspects to how we approach the problem. And this progressive idea, I think, is really important to having an effective approach. So right now, this client-side render, it has some of these screen space ambient occlusion technologies where you're getting some of these features like shadows. So for everyone else who's not as familiar with rendering and visualization and scientific visualization, the context is that there is a set of libraries and drivers and approaches based on rasterization. That's more the traditional old school, and that's where you can do your traditional rendering like we see on the left in this slide here, and that has a certain number of capabilities. The new school is more of these approaches, these algorithms that are based on ray tracing. You've heard these technologies, kind of ray tracing and path tracing, and the idea is where you're tracking more like the physics of light and how it behaves in a system and simulating that effectively, how light is interacting with the data. So you get something that's more realistic and more effective, more beautiful, really, in your rendering. But the software and the hardware stack and the hardware capabilities are quite different. And so right now we take this this approach with our data is that use this traditional raster technologies that's available everywhere, and you can get some limited capabilities to it, and take advantage of that because it's important that everyone has access to that, and it can give you it definitely gives you value. At the same time, these new it requires more compute power, different software, oftentimes a GPU. So that's what's really exciting, and kind of making that available when it's available is exciting to me. So a lot of the focus is, I think my focus is making that available, but progressively available, because you can generate these beautiful images that are beautiful, but also, like you said, I agree, having these shadows, you can really see more in your data. And I defer to different groups that are working on the rendering algorithms for that, like Dan at the Allen Institute. But what I think is really exciting that my focus is on is making that available when it can be available. And that means, what does that mean? That means providing these remote rendering capabilities on these other systems that have the GPUs and the software available. That means also pushing for support for some of these new technologies like WebGPU that's going to support the ray tracing and the path tracing through these compute shaders. So, you've heard of this technology, WebGPU. It's really exciting. It's coming. It's not like on Linux. Sadly, we don't get access to it in the default BIOM browser, but it's coming to be supported on all browsers and different platforms. And what I think is really exciting from a scientific perspective is access to the GPU. Certainly, there's a lot of compute power there, but it's finally made standard and in a standard way access to these compute shaders. So GPU, the software stack, and the hardware stack, there's great support over many years for rendering, visualization rendering, because everybody loves a game. Everybody loves rendering their data with this, and that's mostly still focused, the rendering side, on this rasterization. But you can use these compute shaders to do these more physically realistic algorithms that try to model the actual behavior of light with these compute shaders. And you can also use these compute shaders to do things like general purpose computing that you had to go to things like OpenCL in the past, but now they're available everywhere, and you can do things like our processing on them. So I think that those areas are really exciting, and I'm excited to see these ray tracing and path tracing capabilities come in a progressive way as we provide this data remotely, and as the web technologies, WebGPU specifically, and the SIMD, which is already available and we support in ITK WASM, become available. You can also use the SIMD for doing some of these very expensive ray tracing operations.
Great. I have more questions, but Conrad, maybe you should ask yours first.
So first of all, thanks, Matt, for that great presentation. There's a ton of stuff there. Awesome looking technology, and at one point you alluded to server-side rendering, and I was curious about that. I ran into like NVIDIA Index at some point that promised to do something similar, but I never got it to work. So I was curious if you have any working implementations of that, and is there anything that we can try out?
Yes. So right now the Agave is something that we don't have like a demo up, but it is working. And yeah, setting up the software stack and the systems too can be quite difficult and sometimes kind of buggy approach or just experience, like you said. So we do have something set up where with Agave and using this ImJoy Python client, which is very easy and nice to work with, and then our client-side WebAssembly and server-side WebAssembly and JavaScript and Python interfaces talk to it, and then we work with the rendering that is done. Like with Agave, they support generating and using a Docker image, which can be helpful sometimes. It can also, also kind of run into limitations, but it's getting better and better. The NVIDIA support for working with these systems in technologies like Docker. And there's other rendering, path tracing, ray tracing libraries out there that I'm looking at. One of the really interesting, promising systems is Inari, which came out as kind of a WebGL or WebGPU standard, but for API interface for scientific computing that NVIDIA and AMD and Intel all promise to support. That project it's taking time. Standards and people coming together, it is taking a lot of time, but that's another one to keep an eye on. That is again focused on this ray tracing, path tracing, process to visualization. And then there's some other libraries and implementations out there that I think are interesting. I had to kind of look them all up now too, but generally the approach that we're taking with the tools and working with these is that you are sending, like we have with OMIZAR, basic messages that are JSON, standard web technologies, and then the rendering happens in a black box, and you're getting a rendered screenshot, essentially a frame, and then we're rendering the frame for the client. And we're trying to standardize on the data that's coming into the system with OMIZAR. And that's kind of the general approach. And then as these technologies and libraries and different options, not kind of betting on a single one, come to the forefront, we can use them.
Very cool. Thank you.
I've got a quick question. This is John Bogovic at Janelia. Thanks for everything, Matt. That was really cool. I guess I also wanted to say I've been using ITK widgets pretty recently. In particular, you're still there, right? I'm seeing Conrad on my screen. But anyway, thanks for all of the technology and for being a part of the community, because I know we all really appreciate that. My question is about, I guess, the coding part of the talk. In particular, it was nice that you touched on how one might, oops. Oh yeah, this is nice, hi. I appreciated how you touched on how one might create one of these web applications from different pieces written in different languages. But I was hoping you could expand on how, for example, you might use the infrastructure that you've set up to say, write a web application that enables on-the-fly simple image analysis, things like, let's say, simple non-learning based segmentation methods. I guess, in what languages would you write what pieces? How would you structure the web application so that a user could, for example, click on something in the web application, it triggers some simple segmentation method somewhere, and that renders the result. Thanks again.
John, are you essentially asking how you would do Napari in the web?
I mean more general than Napari, I guess, because I'm not just what Napari does. I mean, Napari does a lot of things, but if I was gonna write some segmentation method, or I guess there's two parts of the question. One is, in what language would you recommend I write low to medium, low level algorithm? Should I be writing stuff in Python or C++ to use your technology? And in what languages should I be writing the user interface? Or in what languages would you, if you were going to be doing this tomorrow, write the user interface stuff and the lowish level code that does the segmentation stuff? That's more what I'm asking.
That's a very good question, and yeah, thank you again, John. It's great to see you, and thank you for all the work that you've done on the OMI. Especially these spatial transformations that I'm really excited that we have in the community, and work with things like registration. And I know you've done a lot of great work with the registration pieces at Janelia there, and kind of the goal there is for example to have some of these, maybe some of the registration components we've written in ITK and C++, but also call them and use them in Java, and set up a pipeline that uses some other functionality that's written in Java, and get a full fledged processing pipeline that has these different languages working together. That's kind of the dream. And in terms of how to do it, yeah, a lot of brings up new challenges, and you're not just doing, when you talk about bringing together something like C++ and Java that's more focused on performance, and then something that I would write my interface in JavaScript and HTML because that's nice. Maybe my overall coordination logic in Python, and then have some of the high performance pieces written in C++. And that's what would be very effective, I think, for bringing together a processing pipeline. And I've learned a lot, and I think the whole computing ecosystem has learned a lot, and it's put into practice in some of these web technologies, specifically trying to make possible WebAssembly in WebAssembly, this idea of the WebAssembly component model, and then also this idea and some of the ideas that you see in WebGPU. So first with WebGPU, and there's a few really interesting blog posts on this from a high level, maybe from Google. I read it one recently, but how do you make all these systems work together? And the web is also very asynchronous, which causes different issues and programming problems. And we have these challenges also when we're talking about like distributed computing too. So asynchronous, distributed computing, and the approaches that they've done in WebGPU, you look at the differences. What's the difference between WebGPU and WebGL? Well, they use these best practices in terms of how things are architectured. In WebGL, there's a lot of this global state that affects everything everywhere. In WebGPU, they try to avoid global state, and they have immutable pipelines that you generate that you work with the system. So these practices are working with immutable pipelines, a transition from object-oriented programming where everything is connected together in a very complicated way towards functional programming paradigms. And the WebAssembly component model, the approach that is advocated there, that works well there, that's performant, has easy reason about applications that can work with each other, is also something like the actor model, this paradigm in programming where you have different WebAssembly modules, maybe written in different languages, and they interact by sending messages, and they all manage their own state, or they behave like a pure function. So what is facilitated in these ecosystems, these web platform ecosystems, is a model that's more functional programming, that's more, I saw one description in a talk recently of, it's like microservices, which the broader computing industry uses for something that's scalable, a scalable architecture. For these very large organizations, microservices are very popular, but something that's actually performant with these, using things like WebAssembly. But it's this idea of really a focus on managing state that's using architectures and paradigms like functional programming, like the actor model, like finite state machines. So that is also something that just makes things scalable, easy to reason about, easy to understand, and work together in a nice way. Interoperability in terms of your program architecture in addition to the technologies. So that's been really fun and learning about. And I think if you look at the WebAssembly component model and a lot of which is something that I'm working on supporting, it's coming. It's expected to be released after many different experiences over iterations over many years in the next few months. Some of the new versions are coming out, but that they use these approaches. So yeah, what I would love to working towards with these approaches is you have a nice user interface written in JavaScript. You're coordinating it with Python. These high performance things in maybe C++ or Java, and then it all working together in an easy to understand way where state is managed. That's the dream.
Yeah, thanks so much.